Okay, hello everyone and welcome to today's webinar. Thank you for joining us. The title of today's webinar is Remote Sensing Solutions for Defense and Security. We're excited to share with you the insights needed to turn geospatial imagery and data into timely, accurate and actionable intelligence. So let's get started. The time is 10:01 in the UK, 11:01 Central European time. My name is James Slater. I'm the EMEA channel manager at L3 Harris Geospatial. I'll be the moderator on today's webinar, and I'm excited to be joined by Nikolai Holzer, sales engineer at L3 Harris Geospatial. So Nikolai and I work closely in collaboration with customers and partners throughout Europe, Middle East and Africa. And we really focus on delivering geospatial solutions optimized for our customers' needs. Where I have the day-to-day oversight, Nikolai provides the specialized technical pre-sales and engineering support to our business. We both have a strong background in geospatial, my own in GIS and remote sensing, holding a BSc in GIS from London Kingston University. Nikolai holding an engineering degree in cartography from the Dresden University of Technology. Just a couple of housekeeping items before we get started. I've muted the phone lines for all attendees, so if you have any questions at any point during the webinar, feel free to enter them into the chat box and we'll try to answer these at the end of the presentation. I also need to let you know that we're recording today's session, so if you don't wish to be recorded, feel free to drop off. Okay, next slide please, Nikolai. I'll talk you briefly through today's agenda. We've scheduled just 1 hour for the webinar today, so I expect we'll move quite quickly to cover everything that we want to show you. I'll start off with a quick overview of L3 Harris, and we'll get on to examples and use cases, which is really the bulk of what we want to talk to you about today. And that's really the what of what we do, before we finish with the how of what we do, how we deliver these solutions. So yeah, before I get into the detail, I'll talk to you a little bit about L3 Harris Geospatial, which really is a mid-size US defense technology company, specialized in delivering end-to-end solutions to meet our customers' mission-critical needs. We're split into 4 segments. And the part of the business that you're talking to today, L3 Harris Geospatial, rolls up under Space and Airborne Systems as the leading provider of solutions that extract meaningful information from all types of remotely sensed data, including SAR, LiDAR, and optical systems. We apply our expertise to deliver transformational decision-making capabilities for end users in the defense and security domain, also in agriculture, transportation, utilities, and other markets. Next slide, please. So to give you a bit of a background on L3 Harris Geospatial and our work in defense and intelligence, this slide really provides a good overview of that. We really feel that today remote sensing solutions combined with geospatial analytics are becoming a really safe, accurate, robust, and often low-cost approach to automate operations that can provide critical insights faster and with a higher level of accuracy than ever before. L3 Harris really has a 50-year legacy in the defense and intelligence geospatial domain. So we have both the experience and the advanced end-to-end solutions to collect, manage, and leverage primary data collects, providing time-critical insight. Time-critical insight really needed to make effective decisions quickly. So some examples we're going to touch on today include multispectral anomaly and target detection. We'll talk about hyperspectral material characterization. We'll go into a bit of a deeper dive into deep learning, our deep learning technology for object-based classification and the utility of this. And we'll also describe our SAR-based detection, characterization, and wide area monitoring solutions. Yeah, we'll touch on really both use cases and operational examples of each of these in today's webinar. Next slide, please, Nikolai. So just one final comment from me before I hand over and we really kick off today's webinar. And I wanted to just give a quick shout out to our partners. As I mentioned, L3Harris has a history of delivering flawless execution on some of the world's most demanding space, defense, and security programs. And we do this for customers including the US Department of Defense, NASA, NOAA, and the National Geospatial Intelligence Agency, the NGA. This coupled to our class-leading position in image science and our commercial off-the-shelf technology, we feel really enables us to bring really market-leading and bespoke solution iterations, which we can tailor for specific needs. We do this in a robust way, in a seamless way, and in a way that gives a high level of control over our application integration and execution. I want to also recognize the imperative that we have really with our customers globally to deliver full project lifecycle value and to do that across the enterprise. And really with that in mind, we make sure that we partner with the world's leading domain providers, data providers, and integrators to provide robust sensor support, availability of our technology, and integration into the world's leading and the wider C4 and C5 ISR platforms you'll all be using. So that's enough from me. I'm now going to turn the webinar over to Nikolai to get into the detail. So over to you, Nikolai.
Thank you for the introduction, James. My name is Nikolai Holzer. I'm a sales engineer here at L3Harris Geospatial. Thanks for joining the webinar. And yeah, I will now be happy to show you some real-world examples and use cases that have been derived with our L3Harris Geospatial technology and that enable the defense and intelligence chain to make faster and more higher confidence decisions. As you saw on the agenda, the first part of these will be more focusing on imagery and LiDAR, and the second part then on synthetic aperture radar. So remote sensing technology is used extensively in a wide variety of military and intelligence applications, some of them which are listed here in this slide. Yeah, typical military and intelligence applications include, for example, to locate specific targets, and this can be by shape or also by spectral properties. And we will show you more examples regarding that. Also to detect particularly hidden targets, for example, tanks that are hidden under 3 canopies, and to analyze terrain as well. So elevation images, for instance, can be used to find steep areas and passes, areas that are difficult to reach, and line of sight analysis can determine which areas can see and can be seen by field personnel at known locations. Yeah, and in many cases, military, of course, they have access to better images, more advanced sensors that are available to the non-military personnel. So let's have a look, a more detailed look on some real-world examples. Location of specific targets of interest, for example, and determining what spectrally unique material exists in a scene. So this is material identification, are 2 of the most common scenarios when we work with the spectral information of image data. And here we work with hyperspectral images. Hyperspectral data and hyperspectral analytics is used in various fields in defense and intelligence, for instance, particularly to identify man-made objects, for example, on the ground, based on their spectral signature, such as, for instance, a military vehicle. Here in this slide, you can see a screenshot of ENVI, our image processing software, that has many methods for matching image spectra to reference or to library spectra. And in this example, we identify material based on the spectral characteristics and rank the match and rank them to an unknown spectrum from a spectral library. So this position, we would like to understand what type of material or what type of object this is here on the ground. And you can see here the spectral profile, so going through the entire spectrum of that hyperspectral image. And then we get here a plot of pixel values at every wavelength. And then we visually and quantitatively compare that to spec libraries to identify the spectrum on the fly. So here, for example, it was identified for material identification that this is a galvanized steel metal. So it's a type of roof. Yeah, when we go further with material identification, we can classify entire scenes based on their spectral characteristics. And some of the best examples that showcase the power of remote sensing involves here, as you can see in that figure, mineral mapping with imaging spectrometers. In this example, we at LC Harris, we have been proud to support the US Geological Survey in their efforts to assess the natural resources of Afghanistan as part of the project Oil and Gas Resources Assessment in this region. So this example highlights the capabilities of image spectrometers that measure discrete bands across a reflected portion of the electromagnetic portion. Yeah, and this gives us a powerful technique for mapping the distribution and relative abundance, here in this case of minerals, but this could be also a vegetation type of classification, depending on the purpose. Yeah, when we go further, we can run anomaly detection in order to find objects that don't belong to a scene. So anomaly detection is a process that is performed in images in order to highlight significant or unnatural spectral differences in pixels versus neighboring values, as you can see here in the black and white images. So the anomaly detection, it extracts anomalous targets that are spectrally distinct from the image background, and that could be hidden from the human eye, as you can see on the right side in the multispectral image. This type of anomaly detection is very useful in determining things such as disturbed earth or spikes in energy level versus surroundings, for example. And this could be subtle spectral features such as, for instance, concealed targets by tree canopy or camouflaged military vehicles. So this process is useful in narrowing down searches to determine if and where further investigation is needed to quickly create situational awareness and to reduce time spent on scanning imagery by really putting the focus on spectrally anomalous objects that would normally not belong to the scene. Such as, again, for instance, as the example here, a camouflage, a vegetation camouflage in this vegetation scene that cannot be seen from human eye, but that due to the spectral abnormality, it is possible to determine with anomaly detection. Target detection is the second main approach when working with spectral information. So we here go vice versa. We have specific objects that we would like to find in a scene. Previously, we wanted to understand what type of object is at its specific position in a scene. Spectral target detection finds targets in multispectral or also hyperspectral images by finding pixels in an image that are matching the spectral signature of a target, such as here in this example, man-made objects, including aircrafts, camouflaged military vehicles, tanks, or other material targets. So this particularly allows us to locate targets that could be hidden from the human eye, again, by tree canopy or any obstruction. Targets can be also detected when features and backgrounds are similar, for example, to identify potentially hidden true positions and approaches to targets. So in this figure, you see the spectral signature of 3 different types of targets that we would like to detect. You see they are spectrally distinct, and And when we compare these spectral signatures from these objects with spectrum at pixel positions in multispectral hyperspectral scenes, we are able to find this specific type of targets. Yeah, this is the target detection, material identification based on spectral analytics. Deep learning is another type of approach. Deep learning is also considering the spectral characteristics of objects, but in image terms, when we work with convolutional neural networks, we look more on the shape type of the feature, so at the convolutions. A common use of deep learning in remote sensing is feature extraction. So this is identifying specific features in an image, such as, in this example, vehicles. But this could be also, beside of cars, it could be also military vehicles, aircrafts, tanks, or other type of utility equipment. Yeah, in this specific example, our deep learning technology is used to count the number of cars in store parking lots to create monitoring and alerting services that helps stores to predict future trends. But in a military context, such an example is particularly of interest for activity monitoring and to detect significant changes in areas of interest over time. Through a process that is called labeling, locations of specific features we are looking for are marked in multiple images. And then with training, we pass that labeled data to a deep learning model that learns what a feature looks like. And finally, the trained model that can then be used for more or same features in other images, having similar features, having similar properties. So this is the classification step in order to find specific type of objects. Another example here, which is pretty difficult with spectral, based on spectral characteristics, is to extract the road network from image data. Now, roads can be very difficult, can be very different. There can be asphalt roads, concrete roads, or just roads covered by dust or dirty roads. And deep learning provides here an approach to train the specific characteristics of how roads look like in order to extract them. So in this example, we work with 3D information from a 3D point cloud, but we derived a digital terrain surface model from this point cloud. So you see an RGB image here with height, intensity, and shaded relief from the point cloud information in Mombasa in Kenya, where we are able to derive 3 different types of roads that you can see here on the right. Speaking about activity monitoring, activity-based intelligence, another implementation example is monitoring activities at an airport in order to analyze temporal patterns in time series remote sensing data, such as detecting airplanes over time and also determining busy airport locations. And we here developed an activity-based intelligence system, which is based on our enterprise solutions as part of a project for the UK military. And this involves taking in large quantities of data, automatically process them, and generating geospatial features as an output. And one of the outputs is here such a dashboard. So planes are extracted from the heat map. Deep learning is running in the back in order to detect these airplanes and stores them as geospatial features in a database so that we can query for these features easily and collate the data on a dashboard. And this dashboard has many widgets, as you can see, and is showing 1 month of data here at an airport in the UK. And what you can see here in this time series axis is particularly how busy the airport is during 1 month. Busy locations at the airport. You see peaks at the weekend, particularly a high peak here at the weekend beginning of August, which marks the start of the vacation period. Analysis of terrain is another typical use case and an area where remote sensing data can provide an added value. Analyzing terrain is important to find areas that can be passed or that can't, that are inaccessible. And line of sight analysis can then help to determine which area can be seen by personnel. So here you see a digital surface model and derived viewshed analysis of our technology from various heights and various directions in the field of view. Here an area visible for an observer at a specific location at a height of 80 feet. So now we can see the same observer point, but we added areas that are not visible for that person at that point. So, and we also added distance rings at a defined radius of 250 meters. So it can now be limited the view of the observer to a specific direction with horizontal and vertical view limitations, and added a second point at a height of 107 feet. And this display shows the coverage from both towers in the image, from both observer points. And this can also set to show only the areas that are viewable by both observer points simultaneously. And it can be seen that both observer points can't see each other. Another example, finding potential activity and inspect suspicious activities in an area of interest. Assume that military intelligence reports suggest activities in a particular area of interest, for instance here in the western portion of Iran. And the goal is to derive actionable intelligence from imagery to understand what is happening on the ground and where anomalous activities are happening. So the first step is typically to derive analytic-ready data as a first step. Includes auto rectification, punch sharpening, for instance, atmospheric correction, image co-registration, and so on when we're working with time series images. And then based on that analytics ready data to derive thematic information that gives us the intelligence that we need. Here in this example, line of sight communications, line communications, roads in red, also change detection in blue, and anomaly detection in green. And the goal is to identify areas or if there are any areas that both has changed and become anomalous. And we could identify here one area that both changed over time and it became anomalous based on the previous examples that I have shown you, anomaly detection, material identification, and then easily a report, an intelligence report, can automatically be derived and delivered to incorporate, for example, into the daily update brief. Now, let's speak about some use cases and examples from synthetic aperture radar. Cloudy skies, dust, and other vision obscuring conditions often limit the support capabilities of overhead aircrafts that can't provide warfighters on the ground. Airport weapon systems that use electro-optic or infrared sensors during support missions can't see through clouds, and SAR can here help to overcome that limitations. So one of the main benefits of SAR is that it can see through clouds and that it can work during day and nighttime conditions. And this is particularly useful for automating processes over time, because every image in a SAR from SAR can be used because of this independency of cloud coverage and day-nighttime conditions. Here you see some typical examples of SAR for D&I applications, and I would like to show you now some more in detail. Most of these use cases have been conducted by our partner SARmap in Switzerland. SARmap is the company that stands behind the ENVI SARscape analytics that are incorporated in our technology. A typical example here, also conducted by SARmap, is ship detection. Ships can be detected in SAR because of differences in how the radar signal is returned back to the sensor. So there are different types of backscatter depending on the surface structure, depending on how that interacts with the surface. So smooth water bodies, such as here on the ocean, they produce so-called specular reflections, so away from the sensor. which creates its dark pixels in a scene. So you can see here smooth water bodies as black in the SAR scenes, and ships produce a double bounce, which returns most of the radar signal back to the satellite, and this returns in pretty bright pixels. So in addition to detecting ships in a SAR image, which works pretty well, of particularly value is to use AIS, so automatic identification systems, to compare the results. Since 2003, all vessels over 20 meter, 300 gigatons, must be equipped with a SAR with an AIS transponder. And while these AIS beacons are required to transmit on all large ships over times, sometimes ships turn these signals off, or they alter them to report a different location. So the combination of SAR ship detection and AIS tracking can identify ships where both in the SAR scenes ships have been detected and where an AIS signal has been sent, or where this is not the case. So here in this figure, we see the yellow crosses. These are ships that have been detected from SAR. We see the overlaying AIS track in purple and the match. But there are some ships that have been detected in SAR, but they do not send an AIS signal. So this is an anomaly. We have here identified dark targets. And the reason is, yeah, and the question is, what is happening? What is happening here? What is happening with the ships? AIS is spoofed or disabled because of many reasons. One of them is illegal, unreported, and unregulated fishing. This is a big problem. 1 of 5 fishes, for instance, are caught illegally. Sanction violation is another problem. AIS, for instance, is particularly turned off close to sanctioned countries, for instance, North Korea, Iran, or Syria, and others. And for instance, oil tankers are often close to such areas that have their AIS turned off. Or illegal oil spilling is another problem. Oil spills, by the way, can also well be seen from SAR, a typical use case when AIS is spoofed. So yeah, the main motivation is maritime domain awareness and border and asset monitoring for such type of dark vessel detection, or to detect anomalous vessel behavior. Here a case study when speaking about ship detection, also case study from our partner SARmap, monitoring port installations at a new container terminal in Djibouti. You can see here in the figure that single ships can be pretty well automatically detected date by date, and also based on parameters like length, width, and heating measured. So this animation here is obtained from almost 140 Sentinel-1 acquisitions in the 2015 to 2019 period. On the left, you see statistics about the average monthly activity that can be estimated for the whole area that you can see in that figure. But it could be also for sub-regions, for example, close to the new terminal, and we will do that later in the next slide. And we can also clearly detect here in such a figure seasonal and yearly trends. Here in this case study, speaking about this new container terminal, this has been completed in 2016, and we can see that as end of activities that is well visible in the SAR amplitude time series that you have seen in the figure before, when there have been no ship activities during the construction. So the area of the new container terminal is shown in the oval shape here. And the time series shows the construction of another little elongated harbor just southwest of the new terminal, which was initiated in 2017 and terminated beginning of 2018. Again, this figure here on the right, this is a false color composite. This image is derived from the multi-temporal stack of images that you have seen before. And what information can you extract from such an image? Red represents the coefficient of variation of backscatter over time in the time series, with mean in green and the gradient in blue. Typically, if the mean dominates, so the mean backscatter over time in a time series, this indicates stable areas, so no activities. Feature gradient in blue, so this means sudden changes of backscatter over time in subsequent series, indicates sudden changes in an image. And you also see the ships here in purple, combination of gradient and coefficient of variation, meaning also changing ship's position over time. But again, particularly of interest is here this new container terminal that appears in blue, in bright blue, indicating sudden changes at this area. The statistics image on the left is covering that new container terminal area. Again, what we can see here in the statistics image are increasing activities in 2018 in this AOI. And activities that started in 2016. So again, they started in 2016 because the container terminal was terminated, but then also of interest, these increasing activities from 2018. Yeah, and part of this new container terminal has been identified as a military base, another military base under construction, and that was completed and is active since 2018, as investigations have found out. Yeah, it's a slow rising cape and is built just adjacent to this new Chinese-owned commercial port. Here's a screenshot from Wikimedia that describes that as a Chinese naval base. And there are also some comments there, also giving names of military vehicles, airships that can be seen, probably identified from some very high resolution optical images. So the statistics that cover that little AOI, just around the little elongated harbor visible in Wikimedia, that you can see here. So from the red polygon with the two red white circles, show increasing activities, particularly when the Chinese naval base then became operational in 2018. Another case study here on monitoring, on change detection, is oil smuggling activities here in the Omar oil field in Syria. It has been found out that oil smuggling happened at that place when it was controlled by the Islamic State, by ISIS, which was a form of financing for IS that allowed them to accumulate significant financial resources for the purchase of weapons and ammunition in significant quantities. So in December 2015, the coalition forces have launched an air offensive to regain ISIS-controlled areas that have fueled oil smuggling. Again, here on the left, you see an intensity time series image with the same parameters, coefficient of variation in red, minimum in green, and the feature gradient in blue. And it shows area which are changing over time, over the time period of observance. With the pink color that indicates the changes. So something that was there at a certain time and not there afterwards and so on. So an assumption that is here that these are most likely truck routes. So someone there was smuggling oil, maybe for providing it to the populations. And some evidences later have been demonstrating that these smuggling activities have been conducted in order to provide financial support for the ISIS activities. And on the right side, you see an optical image of the same area. Almost impossible to extract such information from an optical image. So again, the purple indicates changes over time. These are truck roads. You see the oil facility in Aden in Yemen on monitoring the ground activities at the airfield and at the harbor in Aden. yeah, in Yemen, civil wars ongoing since 2015, and there are hard battles that took place and that still will probably take place in the city of Aden and its airport. You can see in these figures on the right, again, a false color composite image in both geometries, so an ascending and descending acquisitions derived from two multi-temporal stacks. On the left, you see the corresponding amplitude animation figures. Over time from that, these false color composites have been derived. Yeah, what you can see in the image are strong radio frequency interferences. They're well visible in both geometries, and the area where the direction of propagation of interferences cross is quite stable. And these strong radio frequency interferences, they're not constant over time. Yeah, and the area where these interferences crosses, this has been identified as a former missile camp. So the question then arises, are these radio frequency interferences appearing when missiles have been shot from this camp? And we believe that these interferences here may relate both to radar tracking systems for guiding ground-to-air missiles against targets, as well as defending systems, so to identify airplanes or other missiles launched against the base. So in both cases, these strong interferences are quite clear indication of periods of ground activities. And the city of Aden, as said, is being a theater of several battles since 2015 within the Yemen civil war. So again, here from Wikimapia, this means for us that the former indication here should be maybe more read as from time to time active. Again, another study from our partner SARmap. Again, change detection, and again, working with optical images versus SAR images. Again, SAR has unique capabilities on cloud penetration, on night illumination, and it also has a high revisite frequency, particularly because it can penetrate clouds. And this example here highlights how SAR can overcome the challenge of performing change detection in areas where optical data alone is insufficient. So in this scenario, we suspect activity that is taking place. However, our optical analytics is inconclusive. Yeah, SAR is a perfect fit for pervasive monitoring. In this example, here we look at an uranium enrichment facility in Iran, in Fordo. And in this example, we use coherence change detection to uncover surface changes. Here, in order to detect vehicle movements in the desert area that could not be revealed from optical images. Here you see an optical image on the lower left. You see how these PIS roads look like spectrally and also in terms of a shape. It's very difficult to extract such road networks from optical images. This Fordo uranium enrichment facility is located in Iran. And the question is, yeah, which transport networks in this scene are under use? So here you see an amplitude image taken from the 26th of January. And this and the next two slides show how we can highlight very small changes in the order of meters by comparing the amplitude phase from two SAR images. Looking at the SAR image of 26th of January and the 3rd of February, it's difficult to identify any changes in these images. But when we derive a coherence map, we can now see the use of dirt roads and also points of connections that are active between these states. So here we see a coherence shift that is detected, that is caused by textural changes from vehicle tracks in the sand, and this is not spectrally distinct. Coherence, by the way, appears so we speak about coherence when we have the same surface characteristics in multiple images under analytics, and when the surface characteristics are similar in two or more SAR images, it is said to be coherent. Well, on the other side, if the surface characteristic changes, these become incoherent. Incoherent is meaning here darker pixel values, and coherence is meaning brighter pixel values. So you see in this darker pixel values, road networks roads under use in that dust area. So SAR coherence change detection can be used to detect and extract activity which may have insufficient spectral variance for the optical detection, and we are able here to uncover surface changes due to vehicle movements in the desert area. Maybe just on a notice on the upper right corner, these dark gray tracks, this is a flock of camels that induced the area after the acquisition of the first image. And in the center, we see the nuclear plant, which is here. And the frequent roads are visible in dark shades of black. It's an arid region, so the roads are often covered by dust. And this traffic, this leads to decorrelation in this coherence image. Again, a study from our partner SARmap in Switzerland. Another SAR example here on monitoring nuclear experiments with SAR. This example is here based in the United States at a Nevada National Security Site. It's located not far away from the city of Las Vegas. And the site was established in 1951 for the testing of nuclear devices, covering approximately 3,500 square kilometers of desert and mountainous terrain. The final nuclear test detonation at the test site was Operation Julian's Divider on September 23, 1992. And this was just prior to the moratorium that was temporarily ending all nuclear testing in the United States. This divider bomb was a safety experiment test shot that was detonated at the bottom of a shaft sunk. In the figure here, you can see the differences in the SAR amplitude, and this is well visible in the area circled in red, and also well consistent with the known test location. They show the preparation activities like excavation and presence of infrastructure used to lower the equipment. If we would now run some amplitude or coherence change detection analytics, as you saw in the examples before, one would see a clear indication of big changes there, and they're already visible just with visual interpretation in these amplitude images. Now, what we did here, we ran a differential interferometry, so we worked with the phase information. We did interferometric processing, and this allowed to quantify the terrain displacement, here based on ARIS-1 images. We employed differential interferometry and then nonlinear inversion that has been used on the generated displacement map to identify parameters of a MOGI, so there's a point pressure, namely the location, latitude, longitude, height, and also the amount of volume change that through some formula can be converted to equivalent kilotons of the detonation. In the figure on the upper right, you see the interferometric fringes derived from SAR interferometry, and they're already showing the terrain deformation that is caused by this underground explosion. And in the figure below, the inversion of the geophysical models allowed to estimate the position, depth, and power in kilotons of the explosion of that particular example here, Julian's Divider detonation, that could be estimated at a power of some 20 kilotons. Yeah, we have also conducted more recent tests, more recent nuclear tests in other territories. Unfortunately, we cannot show them here in this webinar. This is why we showed that old example of 1992. Again, an example conducted by SARmap in Switzerland. Yeah, and last SAR example on monitoring critical infrastructure, here of a dam in Iran. This dam was completed in 1986, Mosul Dam, and it was built on unsuitable ground. And because it was built on unsuitable ground, it has required constant maintenance to prevent a collapse of the dam. However, when the area fell under control of the Islamic State, it prevented remedial work from continuing accelerating the dam. And this continued accelerating dam instability, putting people below the dam at risk, in particular the city of Mosul and the city of Baghdad. So to analyze the behavior of the Mosul Dam and the surrounding areas in the last decade, we used 4 different stacks of data, two ASA data sets, 20-meter resolution for the period of 2003 to 2010, and then further data sets acquired by the ESA mission Sentinel-1 with 50-meter ground sample distance from 2015 to 2016. And what we found out is that displacements were decomposed along the vertical direction, so an up-down direction, and along the east-west direction, so an horizontal direction. The results along the vertical direction is a indicated downwards deformation with a medium velocity of 1 centimeter per year in the central part of the structure. This is what you can see here in the upper figure. So this means the dam is sinking down, and the results projected on the east-west direction showed that the structure is affected by further rotational deformation, which cause a movement in the east direction, so the water is pushing against the dam. Yeah, it's particularly interesting to notice that clear acceleration of the sinking of the dam here in Sentinel-1 results. So an increasing deformation when the area was under control of ISIS, because maintenance could no more further be done to stabilize the dam. Yeah, and now that the area is secure again, restoration work started in 2016, have been completed just recently in June 2019. And as a result of the restoration, the displacement, so the vertical displacement, as well as the collapse to risk, the risk to collapse has been reduced. Again, a study from our partner SARmap. So now that we spoke and presented a lot of case studies and examples on optical images using spectral and shape information from spectral analytics and also machine learning, deep learning, and on SAR change detection from the amplitude, from the coherence, and also working with the interferometry, so with the phase information. I would now like to wrap up and give you some indications of how we derive that with our technology, with our custom and off-the-shelf solutions that can be found on most analyst systems in defense and intelligence, because they're easy to learn, they're interoperable with common platform, and they're particularly operationally proven. All of the examples that you have seen previously have been derived with our technology, and ENVI, Environment for Visualizing Images, is our flagship product, our commercial off-the-shelf product that can be employed to desktop, cloud, and enterprise environments. ENVI is an image processing and image analysis software that works with any type of data, with any modality. So ENVI supports different modalities, and this includes images acquired from satellite, from airborne, from UAV, from terrestrial, for modalities such as panchromatic, multi, hyperspectral, thermal, LiDAR, SAR, full motion video, all that you have seen before. Working with any size of data, and also in particular supporting raw data format of satellites, including scientific formats, and also including the NITF image format that is widely used among defense and intelligence. Speaking about NITF, an extension to NITF is the motion imagery extension for NITF, which is essentially a container that defines a standard for creating time series in NITF images. This format, called the NV5 the standard was developed to really combine the rich metadata information that is in NITF images with the time series information in full motion video or in wide area motion imagery systems. This standard allows a greater bit depth, frame sizes, number of bands, and ENVI is one of the first commercial software products that supports that NV5 standard. Beside of more than 70 other raw image formats from satellite sensors and from common image formats. correctly importing images, being able to read images, in particular the meta information is one part. Deriving analytic-ready data is another part. Typically, the first step before we start with the spatial processing, we do the spectral processing. Very important is here the particularly for satellite information is the atmospheric correction. So the removal of atmospheric effects from scattering, gas absorptions, removing the solar irradiance curve to convert the raw digital numbers to surface reflectance values. Here you see a screenshot from ENVI, and with atmospheric correction, run in ENVI on the left without atmospheric correction, on the right with atmospheric correction. You see a significant difference in the spectral profile from that multispectral image. On the left, you see the raw digital numbers, on the right, the surface reflectance at this specific position. It's important when working with spectral information, and you saw the examples of target detection, of material identification based on the spectral signature and the examples before. It's of course important to compare apples with apples, so to have pixels in surface reflectance to be able to compare them and match them with spectral libraries. Spatial processing is following the spectral processing. This includes operations such as auto rectification, pan sharpening, everything that alters pixels, also by resampling activities. Very important when working with time series data is to co-register images horizontally, to have them exactly laid on top of each other in spatial terms. Here's an example that was derived from NV image registration, where we not only matched an optical image to an optical image, but a SAR image to an optical reference image. You can see here tie points that have been automatically found in an image, in both images, and then matched to an optical image in order to rob the SAR image accurately to the optical image, to have them overlaid on top of each other for change detection applications. The deep learning examples that you have seen are all based on our technology. While we have experience in deep learning for a longer while, based on our technology, we recently developed a module to ENVI, a deep learning module to ENVI, which is built on TensorFlow technology as well. This is a commercial off-the-shelf software tool optimized for object identification from geospatial imagery, entirely integrated in ENVI, and it stands out by the fact that all is GUI based, so all processing steps are based on a graphic unit interface, including the labeling, the training in particular as well. Here on the right side, you see the GUI for the training, as well as the inference, so the classification. So there's no need to write a single line of code, no need to do any programming. We here hide the complexity of convolutional neural networks for the image analyst, for those that regularly use ENVI, by providing an easy-to-use, seamless user interface to guide through the entire process of the deep learning so creating a data set, training, labeling, training, and classification. The SAR examples are all based on our SARscape product. SARmap, the company that stands behind SARscape developed the algorithm, and this is all integrated in ENVI. Recently, in close collaboration with SARmap, we created more easy-to-use tools for some of the most common SAR processing applications to extend SAR data to more users. So we recently launched NV SARscape Analytics that can be accessed from ENVI, from ArcGIS Pro, and these are particularly designed for the data analyst and not for the scientific user, in order to derive ready-to-use products in one single window. Examples include flood mapping, ship detection that you have seen before, change detection that you have seen before, displacement mapping you saw before as well, time series, persistent scatterers, displacement mapping, and working with Sentinel data. Jagwire is a product beside of ENVI that has as its main purpose to reduce the time from data collection to decision making by providing efficient delivery methods. So Jagwire reduces the time to decision making from data collection through a flexible platform that can be accessed from cloud, mobile devices, and desktops. It's a web-enabled solution for processing, storing, discovering, exploiting any geospatial data, including all common image data formats from SAR, from multispectral, from hyperspectral, from satellite, airborne, and ground systems to full motion video. So it supports virtual any type of data, represents a near real-time federated system, provides analytics on the fly, and enables reliable delivery no matter the situation. It's widely used among the D&I community, and it's particularly used for data dissemination to soldiers, airmen, marines, sailors, and public safety officials worldwide. Yeah, and another example here on deep learning and our enterprise solutions. Helios. Helios is a cloud solution for environmental intelligence analytics from terrestrial camera networks. So Helios detects the occurrence and impact of weather on road conditions and critical ground infrastructure based on traffic cameras. So Helios provides alerts for changing weather conditions. And we used here the Helios technology to build ARGOS, ARGOS automated recognition of geospatial objects. And here ARGOS is a technology that uses Helios and our machine learning, deep learning capabilities to look at particular objects, for example, vehicles, to derive activity-based intelligence. So tracking algorithms are in place that are, for instance, here used to track red cars and trucks. A use case, for example, is to track and locate suspected terrorists after a failed attack plot. For example, witnesses alerted agencies that people of interest jumped into a red car and headed in the direction of a highway. Since ARGOS uses CCTV cameras along highways to identify specific type of objects, such as cars, we can monitor and follow that red car so that the terrorists can be captured. I thank you all for your attention. Here are our contact details, and we would now be happy to answer any of your questions. I see on the time, however, that it's almost 12 o'clock my local time, so there's short time unfortunately remaining. And yeah, so I would like to give the word back to James and see if you're still able to answer one or two questions. Otherwise, feel free to email us, and we're happy to answer your questions individually.
Thank you, Nikolai. A wonderful presentation. So I think, we've had a lot of questions come through on the chat, but we have come to the hour as well. So maybe we'll just address a couple of those questions, and if you can give a brief answer, Nikolai, that'll be appreciated. Sure. So the first question is just on spectral libraries. So are spectral libraries for defense and intelligence applications, are they able to be easily ingested and utilized in ENVI?
Sure, yes, they are. ENVI itself ships with a large amount of spec libraries. It's easily possible to integrate own spec libraries, and it's particularly possible to build own spectral libraries using ENVI, such as for this example here. Of course, if you would like to identify specific type of objects in an image or find specific targets, it's important to have a spectral library that is also matching the image condition to get good fits. Yeah.
Excellent, thank you. And then lots of questions coming through on SAR. But a common question that I'm receiving is about the availability of free SAR data, free global SAR data. Could you recommend any resources for this?
There is medium resolution SAR data is available for free from the Copernicus Sentinel missions. Just check if, I think this was an example also with Sentinel-1. So free data is available since 2015 from Copernicus Sentinel missions globally, having a spatial resolution of about 15 meters and a temporal resolution, depending on the latitude, of about 6 days in Central Europe. If you need higher resolution SAR data, this is commercially available and can go down to resolution of below 1 meter. For instance, Cosmos SkyMet is one example, or TerraSAR X. Please consider it's important, depending on your purpose, what type of SAR data you purchase and use. There are also differences in the wavelengths. So for example, X band versus C band versus L band. Also differences in the polarimetry. So please be careful to really fit your data acquisition to the need that you have. Yeah, that would be my answer.
Okay, excellent. So thank you, Nikolai. Thank you to all attendees on today's webinar. We'll wrap things up now. So that will really bring us to the end of the session today. If we didn't manage to get to your question, then we'll follow up with you afterwards. My contact is on screen now. Take a note of it. Feel free to reach out to me, as is Nikolai's. Yes, thank you for your attention, everyone. Thank you again to Nikolai. And
thank you, James.
Catch you on the next webinar.
Thank you all. Goodbye.
Thanks, everyone. Bye.